Alright, g'day guys. I'll get started with the lecture this afternoon. Welcome back. I hope you all had a good break. I certainly did. I'll just remind you at this stage, straight after the break, first lecture back straight after the break, remember next Monday we have the mid-semester exam. Now, in the next day or so, just keep your eye on the announcements on the Blackboard page. I'm going to just let you know which rooms to go to. So we will have, it'll be during the regular lecture time, but I've got a couple of extra rooms booked just so we can spread out. So some of you will be in this room and others will be in other rooms. So I'll make that clear. I'll post it all on the Blackboard page and make an announcement about that and send out an email. So just make sure you check that in the next couple of days. All right, so we're going to, well, my lectures will finish this week. My last lecture, I think for you guys, will be on Thursday. So I've got chapters 15, 16 and 17 of the workbook to get through now. And then after the mid-semester exam, the next lecturer, Zoltan Neufeld, will take over. So I'll just remind you, before we get into this lecture in chapter 15, because we had a bit of a break, I'll just remind you what we started looking at in chapter 14. We were looking at triple integrals. So we're looking at triple integrals in rectangular coordinates. And one thing compared to double integrals, where I introduced the double integral by considering the problem of calculating the volume below a surface with equation z equals some function of x and y and above some region in the xy plane. For triple integrals, I said that wasn't really a natural way of thinking about it. It's very difficult to visualise hypervolumes and so on. So instead, what I did was talk about mass density functions, and instead, just if you wanted a concept that you could latch onto just at the early stages of dealing with triple integrals, I gave you this, the mass density function. Given a mass density function, that is how the mass is distributed through some three-dimensional region, how we can calculate the mass, and the answer is by integrating the density function over that three-dimensional region. And this is what led us to define the triple integral analogously to the double integral. Okay, so that was in rectangular coordinates. What we're going to look at today, and indeed in tomorrow's lecture, are some new coordinate systems rather than rectangular coordinates. Today we're going to look at a system of coordinates known as cylindrical coordinates. And these are much like the polar coordinates that I introduced for double integrals. Okay, so remember when we started looking at double integrals, everything was in terms of the rectangular variables, right? So the x and y. But at some stage we thought, well, if we have a region in the xy plane, so this is for double integrals, if we have a region in the xy plane that had some kind of circular symmetry or was related to a circle or a ring shape, that would be more naturally associated with what we call polar coordinates. Okay, so we defined a new coordinate system that was much more naturally associated to those types of regions. So the idea is much the same here, but in three dimensions. What we're going to look at are different coordinate systems that have some natural association to different shapes. And I mean, for obvious reasons, we're going to call the first set of coordinates we'll look at today are called cylindrical coordinates, because they'll be a coordinate system that are that's very naturally associated to a cylinder, right, or some kind of cylindrical region in three dimensions. And then in tomorrow's lecture, we'll look at another coordinate system known as spherical coordinates, because they'll be more naturally associated to spherical regions, or regions that have something to do with a sphere. All right, so I guess the presentation in this chapter is much the same as how I presented polar variables, or the lecture on polar coordinates. I forget what chapter of the workbook that was. Was it 11 or 12? It might have been chapter 12, I think, of the workbook, when I talked about polar coordinates for double integrals. Okay, so we'll progress in much the same way. I'll just start by introducing what the cylindrical coordinates are, and then we'll build up an idea of how we can use those coordinates in evaluating a triple integral. Okay, and we'll make some kind of geometric argument and then have a look at a couple of examples later on. Okay, so first of all, how do we define the cylindrical coordinates? So here I've got a three-dimensional diagram, and say we've got a point in space. So this point here, let's say, has coordinates x, y, and z, so the rectangular variables x, y, and z. And what we're going to do is, given those three bits of information, right, the three coordinates x, y, and z that locate that point in space, what we're going to do is introduce this new coordinate system known as the cylindrical coordinates. Now what we'll do is define. You can see I've labelled the diagram with r and theta, and in fact these cylindrical coordinates are very similar to the polar variables that I introduced in 2 dimensions. Okay, I mean there's a subtle difference. Remember we're in 3 dimensions here, so we have to be a little bit careful how we define these variables. Okay, so say I took that point with rectangular coordinates x, y, and z, and I worked out its distance to the z-axis. All right, and this distance I'll call r. All right, so in fact this will be one of my variables, right? One of the cylindrical variables, r, which is the distance to the z-axis. All right, the distance to the z-axis, the distance a point lies to the z-axis. So in particular, because it's a distance, right, because it's a distance, it can't take on negative values. All right, so that's one of the variables. Just, I guess you could make a comparison to the polar variables in 2 dimensions that I introduced earlier. I mean, what I've done here is, in the diagram, just drawn a projection of that line that I've drawn there from the point, so that's the shortest line from the point to the z-axis of distance r, and I've just projected that into the xy plane. And then what we can say is, so that line projected down onto the xy plane makes an angle with the positive x-axis, right? And that angle we'll call theta, and this will be one of our other cylindrical variables. Right, and you can see when we project all this down into the xy plane, it looks very much the same as the setup for polar variables in 2 dimensions. All right, so now the bounds for theta, well, we specify theta equals 0 coincides with the positive x direction, and then as theta increases, right, this line would sweep out the entire xy plane. So as theta increases up to pi on 2, that would then coincide with the positive y direction, and so on, all the way up to 2 pi. Okay, and so in that sense, it's very similar to polar variables that I introduced in chapter 12. All right. So I guess one thing we want to know is, how can we work out the relationship between those cylindrical variables and the rectangular ones? Oh, hang on, we're in 3 dimensions here. I've only introduced 2 variables, right? Remember, we're in 3 dimensions, so that means to specify a point in space, I need 3 bits of information. So now one bit of information is the distance a point lies from the z-axis. The other or the second bit of information is this angle theta. All right, what's the third bit of information? Well, that's the variable z that we'll use, exactly the same as the rectangular variable. All right, so in other words, in our variable transformation, it's exactly the same coordinate as the rectangular one. All right, so you can see here the similarities. Immediately you can see the similarities between the polar variables in 2 dimensions and these so-called cylindrical variables in 3. And once again, you can see at least for values of theta between 0 and pi on 2, you can see immediately from this diagram, at least the projection into the xy plane, that y will be r sine theta and x will be r cos theta, which can then be extended to all values of theta up to 2 pi. Okay, so that's the cylindrical variable transformation. And now what we want to do is use that to work out triple integrals. And in particular, we think because this coordinate system is very naturally associated with cylindrical regions or some regions that have something to do with a cylinder, okay, that's what we'll mainly focus on in this lecture. Okay, so first thing, what we'll do is look at a geometric argument just to see how we can use these cylindrical variables to evaluate a triple integral. All right, so you can see on page 97, I've got this very complicated looking diagram. It looks very busy, and in fact in the next chapter, when we look at spherical coordinates, I'll have a similar diagram that looks even busier. But hopefully, as I explain, hopefully you can see what all these lines and curves are everywhere on this diagram. So I guess the first thing I can draw your attention to is this box. Okay, what we're going to do is go back to the definition, or think about the definition of the triple integral, and just for simplicity, we'll start by considering if we're given a continuous mass density function, how can we evaluate the mass of an object? And what we'll do is just start by making an approximation by dividing the region up into small blocks. But in this case, we won't use rectangular blocks, right? That's what I talked about in the last lecture when I introduced triple integrals in terms of rectangular coordinates. Instead, what we'll look at are these cylindrical blocks or these cylindrical boxes. I don't know, what do you want to call them? So this box, this shaded box that I've got here in the diagram on page 97, is actually part of a cylindrical shell. So I'll just draw your attention to this part of the region that's part of a cylindrical shell. And what we're going to focus on in particular is this box that has dimensions. Okay, so here in the diagram it's written dr. You'll know in my previous notes, whenever I write an approximation, that's what I usually call delta r for a small change in r, and this is what I usually call delta z, for example. So this is the small change in z along that direction. This is the small change in the variable r. Remember, r is the distance from the z-axis. And in this direction is a small change in the variable theta, okay, which sweeps around in the xy plane. Okay, but here I've written r times d theta, or you could interpret that as r times delta theta. So look, let me explain what we'll do. Is we'll consider just, and I mean this is just to keep it simple, right? Just to give you guys an application that we can latch onto just at the start. We'll consider introducing a continuous mass density function that I'll call f of x, y, and z. Now notice I'm giving the function in terms of rectangular variables. All right, I'm giving the function in terms of the variables x, y, and z. Then what we can do is, for the mass of our entire object, so we'll assume that we've got some cylindrical object and we've chopped it up into these small boxes of this shape, right, within each of these cylindrical shells, right? This is just in this diagram. This is just one of those boxes that we'll be focusing on. Okay, so we'll make an approximation to the mass of one box. Okay, remember how we do that, and this is really what I talked about in last lecture. So we choose a representative point inside the box. We assume that this box is pretty small, right? So when we evaluate the density function at that point, which is continuous, if we were to move around inside the box, the value of the density function wouldn't change by much. So just in our first approximation, we'll assume that the mass of one box is constant. We'll assume that the density function, rather, is constant. And in that case, by definition of density function, or at least constant density function, it would then just be the ratio of mass with the volume of the box. Okay, so if I rearrange that, I'd have mass equals density times volume. And that's exactly what I want to write here. So the density function, I've called it f, haven't I? The density function f, evaluated at a representative point P inside this box, multiplied by the volume of that box, delta V. Okay, but then we repeat this process for all these individual boxes. What can I call these? I'll call them cylindrical boxes, right? And then just sum up over all of those cylindrical boxes, right? And here I'll just write cylindrical boxes. We're summing up over all those boxes, and we get an approximation to the mass. Okay, so there's a few things that are outstanding now. So this point, this representative point P in the cylindrical box can have coordinates, say x star, y star and z star in terms of the rectangular variables, or I could give it in terms of the cylindrical variables, r star, theta star and z star. All right? And of course, this is subject to the transformation that we had on the previous page, that x equals r cos theta, y equals r sine theta, and so on. All right, so that's one thing we need to specify. Another thing is, what's the volume of this box? How can we work out the volume of this box? Okay, well, this is one approach. It's a geometric approach, and again, it's pretty analogous to how I dealt with polar variables in 2 dimensions when I gave that lecture in chapter 12. So, okay, let me just highlight a plane in this box. So I'll just add to this diagram. Okay, just to make it clear. So let's say we've got our representative point inside that box. So here's P, and here I've just highlighted, well, you probably can't see that. Here I've just highlighted the plane, so this shaded region here, the plane for corresponding to a constant value of z, where that point P sits. All right? So the idea is P sits in that plane, and this shaded region, I'll just refer to as S when I talk about it in this calculation above. So one thing we could do is work out the area of S, or rather, I'm interested in working out the volume of one box, delta V, is going to be the area of this region S multiplied by delta Z. Okay, delta Z being the height of the box. I mean, okay, in the diagram here it's labelled as dz. I'll just refer to it as delta Z above, though. So, okay, now what we have to do is work out the area of that shaded region S. Okay, and then we've got the volume of one box. Okay, but this is exactly the same calculation we did for polar variables in chapter 12, because that shaded region looks something like this. I mean, this is a little bit of an exaggerated diagram. Okay, so the point P lies somewhere in that shaded region. Okay, so the length here, this is the delta R direction, so that's corresponding, that length there along that side corresponds to a small change in delta R. And then if we work out that distance, and this, to do that, just refer back to chapter 12, but this is just going to be the value R star, which is the distance P lies from the z-axis, multiplied by the change in theta. Okay, so what we end up doing, hang on, let me just, again, this is exactly the sort of thing I did in the lecture for polar variables. What we're doing to make an approximation to this area is to grab these two edges and straighten them out so they're parallel, and so approximate the area of that polar square, whatever you want to call this polar region, as delta R multiplied by R star times delta theta. Right, so it's like the area of a box. So it's just like getting these two edges and straightening them out so they're parallel in this approximation. So in that case, the area of S is approximately R star times delta theta, so that's the length in this direction, multiplied by delta R, and then we've got delta Z here. All right. So that's the volume of one box. So that means this expression I've got for the mass, I can now represent everything entirely in terms of polar variables. Okay, so I can represent the point P in terms of polar variables. Now, if the function that's given, the density function that's given, is defined in terms of rectangular variables, x, y, and z, I need to give that in terms of the variable transformation. So wherever I see x in the function, I need to replace that with r cos theta. Wherever I see y, I need to substitute that with r sine theta, and z doesn't change. Okay? So what we end up with then is an approximation for the mass as just the sum over these cylindrical, I'm calling them cylindrical boxes, aren't I? So the cylindrical boxes where we evaluate that function f at r star cos theta star, r star sine theta star, and z star, and then substitute in the expression for delta v. Sorry, that's the volume of the box. This is delta v. This is what I mean by delta v, the volume of the box, is just r star delta theta delta r delta z. All right, and then we take the limit as delta v goes to 0 and obtain this expression. So the limit as delta v goes to 0, we end up with this identification, or this representation of the triple integral in terms of cylindrical coordinates. All right, and this limit as delta v goes to 0, this limit is taken as delta theta, delta r, and delta z are simultaneously taken to 0. Okay, so this just gives us an approximation to the mass. And remember, in that limit, that's how we defined the triple integral. Okay, so we get exactly the same value. It'll be the triple integral of that function over some region R expressed in terms of rectangular coordinates. But now we've got I guess this is what we went through in the left-hand side of this equation, is what we went through in the previous lecture. The right-hand side is now the derivation that we've just been through, okay, using cylindrical coordinates. Okay, so, I mean, this isn't just restricted to mass density functions, but I did it in that context, again, just to give you a concept or an application that you can work with just when you first meet these concepts. Sometimes that's useful. So one thing I will point out is this, this expression here, that factor R that appears, is what we call the Jacobian of the transformation. So again, that's exactly the same as in the polar variables, right? Polar variables, the Jacobian of the transformation is R. In cylindrical variables, it turns out it's the same. Now, just something I'll mention. In 3 dimensions. Now, I'm not going to derive this result, but it's worth mentioning that this result does exist. In 3 dimensions, if we're given some variable transformation, so we're given some set of coordinates, let's say a coordinate system given by u, v and w, and we've got a relationship between that coordinate system and the rectangular ones, so say where x is some continuous function of the variables u, v, w, and similarly for y and z. So if we have such a variable transformation, it's possible to show that the Jacobian of that variable transformation is just the absolute value of the determinant of the following 3x3 matrix. And so actually it's the same pattern, it's the same type of matrix that I introduced in 2 dimensions. Now we're in 3. So we take the determinant of this matrix. We're in the first row. I just have all the derivatives of x. So first with respect to u, then with respect to v, then with respect to w. In the second row, it's all the derivatives of y in the same order. So first with respect to u, then with respect to v, then with respect to w. And finally, the derivatives of z. And you could check, in our case, so in our case, if you work out that 3x3 matrix using this transformation, okay, substitute those partial derivatives into this 3x3 matrix, work out the determinant, you'll indeed end up with R. Okay, it's much the same calculation as, well, in the case of polar coordinates. I mean, what really makes it easy is because when you take the partial derivative of z with respect to r and theta, those derivatives vanish. And the partial derivative of z with respect to z is just 1. So that third row would just be 0, 0, 1. So anyway, I won't say anything more about that, but that's just how we can deal with the general case. What I've given here on page 97 is just a bit of a geometric argument to the form of the Jacobian, but I just want to make you guys aware that just in general, for a general variable transformation with these given continuous functions x, y and z, you can still talk about the Jacobian of the transformation. Okay, so just a really simple example. I just want to show you how we can use a triple integral. So a triple integral now, right? How we can use a triple integral to find the volume of a region. So to find in particular, to find the volume of a cylinder of radius r and height h. So one thing is that no, it seems to be in focus. So let's call this volume V, and what we're going to do is use a triple integral to evaluate this volume, and we're just going to integrate the function 1 over over this region C, which represents the cylinder. Okay, now why is that the case? Well, remember the definition of triple integral. I'll just mention this in brackets. So if we take the limit as delta V goes to 0, So say we've got some cylindrical region, we chop it up into these cylindrical boxes like we did on the previous page. Right? Now all we're doing, there's no density function, right? I'm not interested in mass density functions. All we're interested in is working out the volume of the region. So if I can work out the volume of these individual boxes, oh hang on, I've already done that in terms of cylindrical variables, and just add those up, that'll give me an approximation to the volume, and then take the limit as the size of those boxes goes to 0, right? We'll end up with this sort of expression. So here, I mean, I'm just using very rough notation, but hopefully you get the idea is that we can use a triple integral to calculate the volume of the region. And this is completely analogous to how we can use a double integral to calculate the area of a region in the xy plane. Right? It's completely the same idea. All right? So we're going to use this triple integral now. Okay, so what's the region C then? Well, this is the cylinder. Now, all we're given in the problem is that it's a cylinder of radius r and height h. It doesn't give us any relationship to any coordinate system or anything like that. So we're free to choose how we're going to relate it to a coordinate system. So what I'll do, I'll just draw up a set of axes x, y, and z, and I'll just choose to place the cylinder. I'll centre it on the z-axis and put its base in the xy plane. All right, so that's perfect for using cylindrical coordinates in that case. If we've got a cylindrical region that's centred on the z-axis. All right, so here's the xy plane. That's the base in the xy plane with equation z equals 0. And because it specifies the height of the cylinder is h, means the top is sits in the plane z equals h. Okay, and what's more, we're told that it has radius r. Okay, so what I can do now is give a description of that cylinder in terms of cylindrical coordinates, right? And you'll see you'll see what I mean when I say cylindrical coordinates are very naturally associated to cylinders. Right? That word "natural" has exactly the same meaning as in the way I was using it when I was talking about double integrals. Right? It means what we should be able to do here is give bounds for all three variables as constant. All right? That's what I mean by natural in this context. All right, so now remember, for any point inside this three-dimensional region, so remember r, in this case, little r, the cylindrical variable, is just the distance a point lies from the z-axis. So r equals 0 puts us on the z-axis, so that's the centre of the cylinder, and r equals capital R. I should have used a different letter, maybe. Anyway, it doesn't matter. Capital R is the outside, like the edge of the cylinder. So any value of the cylindrical variable r that's greater than capital R is not going to be in the cylinder, so I'm not interested in that. So I immediately have bounds on my cylindrical variable r. What's more, I'm interested in all values of theta, so I'm not interested in a slice of that cylinder or a wedge of that cylinder, so I can consider all values of theta from 0 to 2 pi. And what's more, the bounds for z will simply be 0 for the lower bound, so z equals 0, that's the xy plane, right? And z equals capital H will be the upper bound. And this is what I mean when I say these cylindrical coordinates are naturally associated with cylinders, because all 6 bounds I've written here are constant. If I were to try and do this using rectangular coordinates, I would have, well, certainly constant bounds for z, because the region lies between 2 planes, but the bounds for either x or y would depend on the other variable. So I could either give constant bounds for y and then bounds for x would be functions of y. So in that case, or in that sense, Rectangular variables are not so natural. Cylindrical variables are much nicer to use because I have constant bounds. All 6 bounds are constant. All right, so that means I can now apply Fubini's theorem for triple integrals to turn that triple integral into an iterated integral, which is something I can evaluate. All right, so in this case, V is just going to be that triply iterated integral. Remember, that's how we evaluate these integrals. So now I'm just integrating the function 1 here, right? So that's the Jacobian, because I'm using cylindrical coordinates. I've got the Jacobian R. And then the order of integration doesn't matter because all the bounds are constant, so it doesn't matter how I present it. So I'll just take the inner integral to be with respect to z from 0 to h. The next one with respect to theta from 0 to 2 pi. And finally with respect to r from 0 to capital R. Okay, now remember, an iterated integral, we work from the inside out. So this is telling me that I first need to evaluate that integral with respect to z, and then evaluate with respect to theta and so on. However, one thing I can do here is just observe that the integrand factorizes into a product of a function of z by a function of theta by a function of r. Now, the functions of z and theta are trivial. I can take them to be 1, and I'm just left with the function of r as r. And I have all 6 bounds in my iterated integrals are constant. So I can actually use a generalization of that result on page 59, I think it was. Remember at the time I promised I'd be using this result a lot in subsequent lectures. Well, I can even use that in these triply iterated integrals to help me evaluate those. And because we've got that situation here, what I can do is just rip these 3 integrals with respect to z, theta, and r. I can just rip them apart and separate them out and write this as an integral or a product of the individual integrals with respect to r from 0 to capital R, multiplied by the integral with respect to theta, multiplied by the integral with respect to z. Okay, so I'll just make a note. This is a generalization of the result on page 59 that I stated. I haven't offered any proof of that generalization, but actually the proof is very straightforward. So, okay, now it's just a matter of evaluating those individual integrals. What do we... we'll end up with a half capital R squared for this first one, multiplied by 2 pi multiplied by h. Right, just integrating those. So putting that together, we end up with pi r squared h as promised, and as you probably already know, for the volume of that cylinder. All right. Okay, one more example. And this example relates back to that application of using a triple integral to evaluate the mass of a solid object given a mass density function. All right, let's just have a read through the problem first. So it says, find the mass of the solid defined by the region contained within the cylinder, x squared plus y squared equals 1. We can identify that as a cylinder, right, in 3 dimensions. In fact, we can identify that as a cylinder of radius 1 centered at the z-axis. Okay, that guy. So as soon as I see that we've got a region contained within a cylinder, it's at that stage that I think, that's when I'm going to use cylindrical coordinates, right? Because cylindrical coordinates are very naturally associated with cylinders. Okay. There's a little bit more to it, though. So we've got a region within this cylinder that's below the plane z equals 4, but above this paraboloid z equals 1 minus x squared minus y squared. Okay, so it's not a perfect cylinder. In fact, I've got a representation of the region. So here, the top of that region, that's the plane z equals 4, right? That's given in the problem. And the other surface that bounds the solid is z equals 1 minus x squared minus y squared, which is down here, z equals 1 minus x squared minus y squared. Okay, so we're being asked to find the mass. Well, hang on, you've got to give me a density function. Oh, here it is. Okay, the density, the next sentence, the density at any given point in the region is proportional to the distance from the axis of the cylinder. Okay, so I know the cylinder was centred on the z-axis from this equation, x squared plus y squared equals 1. So if I use cylindrical coordinates, that's telling me that the density, so I'll use the Greek letter rho for density. So the density is proportional to the cylindrical variable r. Okay, remember r is defined as the distance a point lies from the z-axis. In this case, because I know the cylinder has equation x squared plus y squared equals 1, the axis of the cylinder, right, the axis of the cylinder is the z-axis. Okay, so in that case, the density at any given point in the region is proportional to the distance from the axis of the cylinder, right? So it's proportional to r. So in that case, so that's just sort of re-expressing what's given in words in the statement of the problem. So in other words, I can write the density function equal to some constant k times r. So k is just a constant of proportionality here. All right, but now we're going to use cylindrical coordinates, right? So we know that the variable transformation is x equals r cos theta, y equals r sine theta, and, well, nothing happens to z. Z equals z. So, in particular, we know that when we take x squared plus y squared, right, that's going to be r squared cos squared theta plus r squared sine squared theta, common factor of r squared, and I'm left with a cos squared theta plus sine squared theta, which is 1. Right, so it means x squared plus y squared I can write as r squared, which means now I can start representing all these surfaces in terms of cylindrical variables, in particular this one, which is just 1 minus x squared plus y squared. Right, I can now write as z equals 1 minus r squared. Okay, so even though it's not a perfect cylinder, cylindrical coordinates are not so bad to use in this case. Oh, and I'll also point out that the surface of the cylinder has equation r equals 1, right? Because we've worked out that x squared plus y squared is r squared, so r squared equals 1, but remember r is a distance, so we can't have negative values of r, so r must be equal to 1. So now we've got everything written in terms of the cylindrical variables. Right, so now we want to work out the mass, or we can work out the mass as the triple integral over that region, I'll call it C, even though it's not a cylinder, where we integrate the given density function. Okay, so now what I want is to apply Fubini's theorem. Right? So this is always the hard part, is working out the bounds for applying Fubini's theorem. I want to turn that triple integral into an iterated integral, which is something I can evaluate. So remember, in the lecture I always spell out this step. Okay, but I mean, of course, feel free in your assignments, even in the exam, to jump straight to writing down the iterated integral. Although I mean, you're welcome to do that, but I do suggest, remember, that in an exam it's all about communication. So if you do put this additional step where you give a description of the region, I mean, that can't hurt, right? It's just demonstrating that you do know what you're talking about, right? Giving such a description for the region as the set of all points with coordinates r, theta and z, such that, well, now we can work out the bounds for r to be from 0 to 1. I mean, just think of all this happening in the xy plane to start with. This is the nice thing about cylindrical coordinates. So think about everything happening in the xy plane first in order to give bounds for r and theta. So remember, r equals 0 really puts us on the z-axis, and r equals 1 puts us on the surface of the cylinder. Right? Anything beyond r equals 1 we're not interested in. It's not inside the region. And we're not interested in a wedge of the region or anything, so we'll take all values of theta from 0 to 2 pi. But now, for the bounds of z, well, if you give me a value, or if you give me values of r and theta in these two ranges, so essentially what you're doing is specifying a point in the plane inside that circle of radius 1 in the xy plane. But now what I want is to give bounds for z, and for any given point I can see that the z value, so I'm just going to draw a few points here. So this point is intended to lie on that surface, that paraboloid, the upside down bowl at the base of the region. Same with this point, and I'm just drawing in a few other representative points. Okay? So I can see immediately that the lower bound for z is just going to be the set of all points on that upside down bowl at the base of the region, which has equation in terms of cylindrical coordinates, z equals 1 minus r squared. So that's going to be the lower bound in this case. And the upper bound will just be this plane z equals 4. Anything above z equals 4 is not in the region, and I'm not interested in. Okay, so that implies the mass. Now that I've got such an expression, it means that the mass can now be evaluated as an iterated integral. Okay? Now, what am I integrating? The density function. So the density function, remember, right at the top of the screen there, the density function is just k times r, so I'll just highlight that. That's the density function. We also include the Jacobian, which is r in this case. And now we're going to integrate, well, with respect to the three variables. But note that I've got this, the bounds for z being functions of r, so that means I'm going to have to integrate with respect to z before I integrate with respect to r for this to make sense. Right? So I'll say I'll integrate first with respect to z from 1 minus r squared up to 4, then with respect to r from 0 to 1, and finally with respect to theta from 0 to 2 pi. Okay, one thing I can do here is use the result again on page 59. This result that I'm so fond of, that I always like to squeeze in wherever possible. This result on page 59 that says, if I've got constant bounds, I can rip apart the iterated integrals. Now, but hang on, I don't have constant bounds, but two sets of bounds are constant. So what I can do is pull out this integral with respect to theta and write this as integral d theta from 0 to 2 pi. I've got a constant k there, so actually I can take that constant outside the integral. And then I've just got this doubly iterated integral that I need to evaluate of r squared dz dr. Right? So I mean, this is just a matter of evaluating those the iterated integrals now. Right, so this is 2 pi times k, so the 2 pi just comes from that integral. And now evaluating this, this doubly iterated integral, I'll just get you started. I mean, this is integrating first with respect to z. So we'll have z r squared evaluated from z equals 1 minus r squared up to z equals 4. Right. You've had a week or so off, so I thought maybe I will go through some of the details here. Now, when I substitute in these bounds, I'm going to be left with just a function of r. So the upper bound, z equals 4, I'll end up with 4r squared minus r squared times 1 minus r squared dr. Right. So this is just 2 pi k integral from 0 to 1. How does all this resolve? That's r to the 4th, and we've got 4r squared minus r squared. So that's plus 3 r squared dr, and maybe that's enough for you guys to verify the final answer as 12 pi k on 5. Right, and I think this is a nice place to stop. So guys, there's cylindrical. So tomorrow's lecture we'll look at spherical coordinates. It'll be a very similar lecture to today's lecture. So I just want to give you a systematic presentation of these two coordinate systems. All right, see you then.